Hello. Today's lesson has a cool name. It's called Aromaticity. If you recall, in our previous lecture, we talked about the cyclohexane and how the cyclohexane, that's that hexagon, is very common in organic chemistry because it is very stable. Right after we talked about the cyclohexane, we talked about conjugation. How if we have multiple alternating double bonds, we can create a conjugated system which is also very stable. So in this part of the class, we're going to combine those two ideas. What if we took a cyclohexane and stitched it together with the idea of conjugation? What do you get? You get benzene. The benzene ring is extremely common in nature, and as you can imagine, it's because we're blending together two very stable things, cyclohexane plus conjugation. If you look at a lot of naturally occurring molecules, you'll find the benzene structure buried inside of them. So for example, phenylalanine is one of the 20 amino acids in your body. And sure enough, there's a benzene ring. An amino acid is a building block that's used to make proteins. So if it wasn't for the benzene ring in phenylalanine, well, you would be not so happy. Another occurrence of benzene in nature is in the hormone estrogen. Estrogen is a sex hormone, and it's produced predominantly by women. We all know about estrogen, but also did you know that men produce some estrogen as well? So don't feel left out, men. But definitely don't feel left out because there is a benzene ring inside of estrogen. So I think we're all thankful for that. And then licarine, now that we are not so thankful for. That also has a benzene ring buried inside, but it is poison found in daffodils. So be careful, don't eat daffodils. You'll be exposed to licarine, which is a poisonous organic compound. So why is the benzene ring so common in nature? Well, that is because benzene has special stability called aromaticity. And notice that I'm not writing out the notes for this first part because I'm going to just give you a little bit of history on benzene so you don't have to write notes, you don't have to copy this down. Just listen and enjoy the story of benzene. And then we will start taking notes very shortly. Okay, so benzene, the history of it was interesting in that it was discovered, isolated, I should say, by Michael Faraday, who's more well known for his work on early electricity studies. So there's actually if you take an electricity and magnetism physics course, you'll find out there's actually a unit in that class called a Faraday, and it's named after this guy, Michael Faraday. But most people don't know is that he was also interested in chemistry. And he was messing around with lamp oil. So it turns out, back in the day, they didn't have electricity to light the street lamps, and they had all the horses and buggies and carriages and stuff. So they had these street lamps that were powered by oil. And so they would be filled regularly with oil and then lit, and that's how the streets were lit at night. So he was messing around with lamp oil and trying to figure out what are the components inside of lamp oil because it appeared to be a mixture. And he found something with the formula C6H6, but he had no idea what the structure of the compound was. They did not even know at the time that carbon made 4 bonds. So a lot of people, very creative minds, came together to try and speculate what might the structure of C6H6 be. And so there was a variety of attempts made to try and draw a picture of what this benzene might look like. You can see some of these look very interesting. You've got this cyclohexane with a line down the middle, or even this prism-shaped molecule. This molecule is crazy. They have these arrows here. I'm not really sure what they're trying to represent with those arrows. I might have to ask a historian, a more historical chemist, more about that idea. But it turns out that Kekule had a dream about a mythological creature, maybe it was a nightmare, called the Ouroboros. And go on Google and search for Ouroboros. I think it's spelled like this, O-U-R-O-B-O, something like this. I may be botching the spelling, but I'm sure autocorrect will figure that out. So the Ouroboros is a mythological creature. It's a snake that eats its own tail. And so it kind of is a metaphor for the circle of life. It's a snake that's like always eating its own tail. And so it's always, of course, regenerating in that sense. So the Ouroboros was this dream that Kekule had. And inspired by this dream, he thought of the structure of benzene being like this, where we've got our hexagon, and that's the 6 carbons, and then we have these alternating double bonds. And Kekulé also, because of his dream, was able to solve a long-standing problem at the time, was that it could not have be this structure, they said, because double bonds are shorter than single bonds. So the shape of the benzene would look oblong like this, but they knew that all the bonds in benzene had to be the same length. So they knew that this couldn't be the right structure. So for a lot of time, they just said, well, that can't be it. We got to keep thinking about an option that allows all the bonds to be the same length. But Kekulé's dream about the Ouroboros, he thought about rapid equilibrium. That is, the double bonds would move around the ring, sort of like the snake eating its own tail, such that they could flip their positions all the time. So all the double bonds could move over one position to create this new structure. And then so on and so forth. They could always be moving such that the double bonds were never quite still. They were always moving around the ring. Today, we know of this as not a rapid equilibrium, but rather simply a resonance structure. And so you may sometimes see benzene drawn like this. That's just a 6-membered ring with a circle inside. Although for this class, I do recommend you draw it with the discrete lines. So he was right. This is the structure of benzene as we know it today. It is the 6-membered ring with the 3 alternating double bonds. Okay. So now we can start taking notes and learn about what is so special about benzene. I mean, it just seems like one organic molecule. We're really going to spend a whole 30, 40 minutes talking about one molecule, and the answer is yes, we will. But why? Okay. So get out your pencil and paper, because here we go. Benzene is not like other alkenes. And they figured this pretty early on. So one of the first tests they did with benzene is an alkene reaction. And we're going to learn about a bunch of reactions in this class, so stand by for that. But let me just show you an alkene reaction that we will learn eventually in this class. And that is, if you take cyclohexane with 1 double bond in it, that's an alkene, and you treat it with elemental bromine, which is a nasty brown liquid. You basically just take the cyclohexene, which is a clear liquid, and you add bromine, which is like a brown-black liquid. A reaction occurs, and a new product forms. The double bond is removed, and it creates a dibromide compound. So the alkene is replaced with 2 bromines. So that was a well-known reaction of the time. However, when they tried this with benzene, thinking that it would work, nothing happened. The benzene stayed the same. It was seemingly invincible to the effects of the bromine, meaning that the alkenes inside of the benzene were not normal alkenes. They were highly resistant to the effects of the bromine. It had an immunity to the bromine. So they knew that there was something special about benzene. So they tried a different reaction that they knew that alkenes could undergo, a reaction called hydrogenation. And you actually maybe remember this reaction from the conjugation chapter, where they took alkenes and they treated them with hydrogen gas and a platinum catalyst. And this reaction deletes double bonds. So just created cyclohexane. And of course they measured the delta H of the reaction, and they found the delta H of the reaction to be negative 28.6 kcals per mole. Okay, they thought, all right, well, let's try this with benzene. Will it work? I don't know. Let's give it a try. They took the benzene, treat it with hydrogen and the platinum catalyst, and it worked, actually. They were able to make cyclohexane from benzene, so seemingly not immune to this reaction. But they did measure the delta H of the reaction, which was highly peculiar to them. The delta H was negative 49.8. Well, that doesn't sound too unusual, does it? Why was that shocking to them? Well, maybe it's better to look at this in a graph form. So let me just draw a mini graph here. Just like we did with the conjugation chapter to try and illustrate this purpose. And so on the y-axis, we're going to have energy. And then along the x-axis, let's draw the different species, okay? So first species we have is the cyclohexane with one double bond. And when that was hydrogenated, it released 28.6 kcals per mole. Okay. Then they did it with two alkenes inside. So something like this. And they found that the energy released nearly doubled. So when they did this, it became negative 55.8. You don't have to memorize these numbers or anything. I'm just trying to show you something cool that they saw about benzene. So before they did the benzene, they predicted, based on this trend, that the energy difference would be negative 85.8 kcals per mole. And this was just predicted. Based on this trend they saw, for each double bond they add, it seems to go up by about 30. But the actual value was even less than the second one. The actual value, because down here is where cyclohexane is, just plain cyclohexane. The actual value was just negative 49.8. So this difference in energy between the actual and the predicted, they did the subtraction and found it was 36.0 kcals per mole. And this savings of energy between the predicted and the actual, this is the actual, is said to be the aromatic stabilization energy. And that is a significant amount of energy. 36 kcals per mole is no joke. That is significant energy savings, and it's all due to this property of aromaticity. So clearly something special about aromaticity that we would like to investigate further, and definitely it interests early chemists quite a bit. Now, one question that I always had is, why are they calling this aromaticity? When I think of aromatic, I think of seasoned, pot roasted chicken. I'm actually doing a pot roast right now. It's very aromatic, these herbs and things like that, but no. I thought I would mention, though, why called aromaticity? This property of stabilization. Why is it being called aromaticity? Well, the answer is that many of early benzene containing compounds smelled strongly. Not all of them, but many of the early ones that were discovered had a strong smell. So it was coined aromaticity early on, but later they found plenty of aromatic compounds that have no smell at all. So the name is just historical. Some examples of compounds that have a strong smell and contain a benzene ring are toluene. This is benzene with a methyl group coming off of it. This is called toluene. And this has a very strong smell. To me, it smells... People always think I'm weird when I say this, but when I was in grad school, I used to use toluene a lot. And I always said it smells like the railroad. So I don't know if that means anything to you. I don't know. Go by a train and smell that industrial kind of smog-like smell. It actually smells quite a bit like toluene. So it's a smell of the railroad. Then was thiophenol. This is a sulfur-containing compound. This compound smells god-awful. It smells kind of like a skunk or something. Very strong, horrible, nasty smell. Something a little bit more pleasant is cinnamaldehyde. This is cinnamaldehyde. This compound smells strongly of cinnamon. So that's actually the active flavor component of cinnamon. So it smells and tastes just like cinnamon because it's found in the cinnamon bark, which they grind up, and that's what cinnamon is. So I don't know if you know that, but cinnamon is actually ground up bark of a tree, and it contains a compound cinnamaldehyde. Well, a big question that chemists had at the time, and this is where we're going next here, is the idea that are there other aromatic compounds? Besides benzene. You know, benzene was the one that started it all, but are there others? And the answer, as you'll see, is absolutely. There are other compounds that look nothing like benzene that have the same property of aromaticity. And I want to show you in this part of the lecture how we can predict if a compound will be aromatic or not. But there are tons of other aromatic compounds, which opens up an amazing world of compounds that all have this thing in common that we wouldn't otherwise recognize. So that's really beautiful that we figured this out as humanity. So the observation that was made early on about benzene was that the aromatic stabilization might be due to conjugation inside of a ring. So we saw conjugation in like a straight line before, but maybe the thought was all you need to be aromatic is conjugation enclosed within a ring. Maybe that is what aromaticity is. So the observation was aromatic stabilization due to resonance or conjugation of CC double bonds in a ring. That was the observation early on. And so the prediction was, let's look at other rings. Might be aromatic. So chemists did what chemists do, and they do an experiment. They're like, well, okay, the 6-membered ring with alternating double bonds is aromatic. Let's try and make a different one. So they first turned to make cyclobutadiene. Cyclobutadiene is basically benzene, except instead of 6-membered ring, they thought, let's go even simpler and just do a 4-membered ring. So this is cyclobutadiene. It's just like benzene, except instead of 6, it's just 4. And it's got that alternating double bonds also. Well, they tried to make it, and nobody could make it. Everyone tried, and everyone failed. So many attempts to make it failed. I mean, they couldn't understand, why is this thing so hard to make? It was finally made in 1965 at 4 Kelvin, which is very, 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 very cold. That's 4K. I'm not talking about your high resolution display you're playing your Xbox or PS4 on. I'm talking about 4K as in 4 Kelvin, the low temperature. And they found that it was very unstable. Extremely unstable. If they warmed it up past 4 Kelvin, remember 0 Kelvin is absolute zero. So to do 4 Kelvin, that was like in a frozen helium matrix. If they heated it up even a little bit, it just blew up. It just fell apart. So why? Why is cyclobutadiene so unhappy? But benzene is very, very happy. So the first thought, of course, was ring strain. Maybe being in a 4-membered ring is just too small. And there's too much going on. It's just too compressed. But this is way, 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 way too unstable to be explained by just that. Ring strain was not enough of a reason why this should be so unstable. There had to be something more. I mean, we're talking 4 Kelvin here, okay? They were able to make the regular cyclobutane just fine without the double bonds. So that compound's totally stable. I mean, it is a little bit strained because of the small size of the ring, but nowhere near what cyclobutadiene was. So somehow adding in those double bonds really messed things up. And so, in fact, in order to understand why cyclobutadiene is so unbelievably unstable, we have to turn to quantum mechanics. Quantum mechanics is our answer. Quantum mechanics explains to us why cyclobutadiene is so unstable. And so let's take a look at a very simple 5th grade, 5-year-old, let's say 5-year-old version of quantum mechanics so that anybody can understand what I mean by that. And so I'm just going to tell you 3 rules of aromaticity, and we'll see how cyclobutadiene fits into that. So I'm just going to jump to the punchline. So, rules of aromaticity. There are 3 rules of aromaticity that have since been discovered. And these are the criteria. This is what you need to be aromatic, and we'll see where cyclobutadiene does not fit into this puzzle. Number 1. The first and most important rule of aromaticity is that you need a closed loop of p orbitals. In other words, we basically need a ring, that's the closed loop part, and we need p orbitals, which means that the hybridization of those atoms in the ring have to be sp2. You need p orbitals and you need the closed loop. This is sort of going back to the idea of we need resonance inside of a ring. Closed loop meaning ring, and p orbitals, that's what you need for resonance. Because remember, resonance only involves the movement of pi electrons in p orbitals. So that is rule number 1, but that alone is not enough. That alone does not make something aromatic. Rule number 2, very important also, in that the atoms of the loop must be planar. Meaning the molecule must be flat, like a pancake. You cannot have any distortions up or down. You can't have any hills or mountains in your molecule. It has to be flat. And that is because the p orbitals need to overlap perfectly. If there's any change in elevation along the molecule, the p orbitals can't overlap and you can't get this rapid delocalization of electrons through these p orbitals. So the atoms of the loop must be planar. In other words, the p orbital overlap is not optional. Okay, the rule number 3, this is where the quantum mechanics comes into play. And this rule number 3 is so famous, it has a name. It's called Huckel's rule. I can never say that without laughing. I feel bad for the family of the Huckels. So Huckel's rule, and it has the U with the 2 little dots over it. That's the U sound. And Huckel's rule states that this closed loop needs to have a specific number of electrons. And specifically, it must have 4n plus 2 electrons, where n can be any number. So if n is 0, for example, then this becomes 4 times 0 plus 2, which is 0 plus 2, which is 2. So 2, if n is equal to 1, then it's 4 times 1, which is 4, plus 2, which is 6. Then comes 10, then comes 14, etc. In other words, it must have an even number of electrons, but it can't be divisible by 4. So these are all the even numbers that are not divisible by 4. That is Huckel's rule. In order to be aromatic, you must have an even number of electrons, but they must not be divisible by 4. If you have 4n electrons, that is, you have 4, 8, 12, etc. In other words, the even numbers that are divisible by 4, we call that anti-aromatic. This is what was going on with cyclobutadiene. It had 4 pi electrons. So it had a property called anti-aromaticity, which is the opposite of aromaticity, which is highly destabilizing. And in order to understand why it's highly destabilizing, we'll have to draw some molecular orbital diagrams. We'll do that in a minute. But let's just take a look at a few examples and decide whether the molecules meet all 3 criteria to be aromatic. If they don't meet the 3 criteria, they're non-aromatic. And if they meet all 3 criteria with this second bullet point, then it's anti-aromatic. So those are the 3 possibilities. A molecule is either aromatic, anti-aromatic, or a lot of the times it can be neither. Let's take a look at some examples. All right, example number 1. 5-membered ring, 2 double bonds. Is it aromatic? Is it anti-aromatic, or is it neither? Well, we have a problem. We have a rule number 1 violation, and that is, what is the hybridization of this carbon at the top? This carbon at the top is sp3 hybridized, so there's no p orbital. How do I know it's sp3 hybridized? Because it's not part of a double bond. If it's just part of a single bond, like there's no double bond connecting to it, then it's sp3 hybridized. If it's sp3, no p orbital. No p orbital, then you don't have a closed loop of p orbitals, so not aromatic. Now, it's not anti-aromatic, but it's not aromatic either. It's neither. Take a look at another one. I call this the stop sign molecule. So just draw an octagon, put some alternating pi bonds in there, and let's evaluate. So it turns out that this seems to meet criteria number 1, in that we have a closed loop of pi electrons. We have a p orbital on every atom. It seems to meet criteria 2. It looks pretty flat to me. After all the sp2 hybridized atoms in this ring would be planar. And let's see Huckel's rule. How many electrons does it have? We need to count the pi bonds. So to figure out how many electrons it has, pi electrons it has, count the pi bonds and multiply by 2. So 1, 2, 3, 4. 4 times 2 is 8. 8 is anti-aromatic. Oh no, but there's a special exception for this molecule and this molecule only, so this won't ever happen. This is a trick question. It turns out that this molecule is smart enough to know that it does not want to be anti-aromatic. It knows how awful it would be if it were anti-aromatic, so it does a trick. It does a hack. It does a sneaky move, and that is that it breaks rule number 2 on purpose to avoid becoming anti-aromatic. And so if you look at this in a 3D form, it deforms itself into a kind of a tub shape. Looks kind of like, I don't know if you can kind of see the perspective, how it kind of like 2 of the sides go up and 2 of the sides go down so that it's no longer planar. Now, you would never be able to predict that it would do this, but the chemists discovered this and they said, oh, now we know why cyclooctatetraene, which is the name of this compound, cyclooctatetraene, is not planar because it's distorting itself to avoid becoming anti-aromatic. This is the only time that you'll need to worry about this possibility in this class. Otherwise, just assume the molecules are planar. Cyclooctatetraene is that one exception. So, rule 2 violation. Thankfully for it, so not aromatic. But if it wasn't for the fact that it broke rule number 2, it would be anti-aromatic. Okay, let's try cyclobutadiene. This was the molecule that they had so much trouble making. It has a closed loop of p orbitals. The atoms in the loop are planar. There's no way for this one to distort. And if you look at Huckel's rule, it has 1, 2. 2 times 2 is 4. That number of electrons is anti-aromatic. That's why this compound was so unbelievably unstable, and they had to cool it down to they had to cool it down to 4 degrees Kelvin just to get it to be formed. All right, one more example on this page. Take a look at this molecule here. Okay. This is pretty good. Okay. This one's kind of cool in that it is an aromatic molecule, Y. It has all sp2 hybridized atoms. They're all having a p orbital on them because all the atoms are part of a double bond. The molecule is planar, and let's count up the electrons. We count up the pi bonds. 1, 2, 3, 4, 5. 5 times 2 is 10 electrons, so that meets Huckel's rule as being aromatic. So 10 electrons, aromatic. The fact that there is this line down the middle doesn't really matter. It doesn't affect the properties of the compound. It's still able to have this closed loop of electrons around the outside, so it is aromatic. Now I want to show you a cool little trick to draw the molecular orbitals of compounds like this, and it's called the frost circle. The nice thing about the frost circle, it will also allow you, when you draw this frost circle, to predict aromatic or anti-aromatic using this diagram. This is called the frost circle. Okay, so let's take a look at benzene here. And benzene meets the criteria for aromaticity in that it's a closed planar loop. And if we count the electrons, we'll see that there are 1, 2, 3 double bonds. 3 times 2 is 6. So 6 meets Huckel's rule as being aromatic. Okay, but let's say I asked you to draw the molecular orbital diagram for this benzene molecule. No problem. You can use a frost circle to do it very easily. So let's start by drawing our axes for our molecular orbital diagram, where the y-axis is energy. And then just draw your compound with the point facing down. So draw your compound such that the point of your molecule is facing down. Very important that you draw it that way. So make sure point is down. Okay. And now what you're going to do, let me just kind of redraw this down here so you can see how it works, because I don't want to decorate the one I just wrote that note on. Okay, I'm just redrawing it. Okay. Now create an energy level of an orbital at every point. So we'll make an energy level here, 2 energy levels here, 2 energy levels here, and 1 energy level here. Do you see what we did there? We just, every point on our shape, we created an orbital level there. And then what I want you to do is draw a dotted line splitting it right down the middle. Just like we saw in the conjugations chapter, everything above this line is anti-bonding, and everything below it is bonding. Now we just copy that pattern over to the right, and it looks like this. Copy that pattern over, and now just label them. Pi 1, pi 2, pi 3, pi 4. Awesome. Now we fill our orbitals up, obeying the 3 rules, the Pauli exclusion principle, the Aufbau principle, and the Hund's rule. And how many electrons are we going to fill in for benzene? 6 electrons. So let's go ahead and fill them in. So 1, 2, 3, 4, 5, 6. Notice how I filled that in using Hund's rule, 1 at a time in the degenerate pi 2 orbitals before I paired them up. So again, I'll show you how I did that once again. Obeying Hund's rule, I did 1, 2, made sure I filled up the pi 1. Then I did 3, and I did not do 4. I did 3, 4 separately. Then I did 5. Then I did 6. And that's the molecular orbital for benzene. Isn't that amazing? That easy? And you can also tell if this is aromatic or not based on this picture. So here's what you can do. You say if all electrons are paired, and anti-bonding orbitals are empty. The molecule is aromatic. I think this is awesome. Okay, let's try a few more examples just to try out this frost circle. All right, let's try to do cyclobutadiene. Can we figure out why cyclobutadiene is anti-aromatic and also draw a molecular orbital diagram at the same time? How many pi electrons does cyclobutadiene have? It's got 4. Remember, 2 pi electrons for each pi bond. Here's my axis. Energy. Now we'll draw our shape of our molecule. Remember to put a point down, so don't draw it like this. Remember, we have to put a point down. That's a common student mistake. So it looks kind of like a diamond when we put the point down. And we'll put some lines. And something interesting you find now is when we draw a red line to split this thing in half, notice that we have 2 of the orbitals are actually on that line. So below the line, remember, that's bonding. Above the line is anti-bonding. If you're directly on the line, you're called non-bonding. The nice thing about non-bonding is you can either have those filled or unfilled. It won't punish you either way. So if the non-bonding is empty, it's okay. If the non-bonding is filled, it's also okay. So it's kind of an optional area to fill. But if you start filling the anti-bonding, you're anti-aromatic. That is not good. And if your bonding isn't filled, then that's not good either. So you need your bonding completely filled and you need your anti-bonding completely empty. But non-bonding is optional. All right, let's transfer this over, our little scheme. It looks like this, and we have a pi 1, pi 2, pi 3. Looks good. Pi 1, we're going to go ahead and fill up total 4 electrons. So pi 1 is totally full. So 1, 2, 3, 4. Uh-oh. This means we have partially filled orbitals. You see how these 2 orbitals are partially filled? They're not completely filled. If you end up with partially filled orbitals when you draw your frost circle and you draw your molecular orbital diagram, that is anti-aromatic. You do not want partially filled orbitals when you're drawing one of these diagrams. Let's do another one. Let's do the cyclopentadienyl anion. So if you look at this carbon here, if you add up the steric number, you'll find that the steric number is 4, and you would expect the hybridization at that position to be sp3. However, notice that we have a lone pair next to pi. So that means that lone pair can participate in resonance. And if an atom can participate in resonance, what's its hybridization? sp2. So because this atom is sp2 hybridized, we do have this continual closed loop of p orbitals, and that's going to be meaning that we can possibly have aromaticity here. How many electrons do we have? 1, 2. Make sure you count those lone pair electrons because those are also part of the pi electron count. Why are those electrons part of the pi electron count? Remember, these lone pair electrons are participating in resonance, so they are contributing to the pi electrons in that they are going into p orbitals. So 1, 2, 3, 4, 5, 6. We've got six electrons that we're going to fill into our Huckel diagram. Our frost diagram. So here's our energy plot, and we'll need to put the point down. Looks kind of like that. And Not perfect, but close enough. And we'll draw our energy lines. And here's our midpoint line. Anti-bonding, bonding. Transfer this over. Looks like this. We've got our pi 1, pi 2, pi 3. And we need to fill in 6 electrons. 1, 2, 3, 4, 5, 6. Oh, great. We have no partially filled electrons, no partially filled orbitals. Everything's fully paired up. So that tells us aromatic. Awesome. That means aromatic. All right, we'll do some more examples like this during the live class, but I just wanted to introduce how to draw the frost circle, and this is called the frost circle. Why is it called the frost circle? Some earlier versions of this actually inscribed the shape inside of a circle, but I just got rid of the circle because I thought it was confusing, so it's still called drawing a frost circle or frost diagram. And it's allowing us to get 2 pieces of information. We're able to get, number 1, the molecular orbital diagram, and number 2, we're able to determine aromatic or anti-aromatic. All right, I want to talk about heteroatoms a little bit, because so far we've looked at aromatic compounds that only contain carbon and hydrogen. But what about heteroatoms like oxygen and nitrogen? Turns out that they have a place inside of aromatic compounds as well. The heteroatoms are interesting in that they can rehybridize to apply their lone pair electrons to the p count if it would help. So it can rehybridize to applying lone pair if it will help. Let's take a look at an example. Okay, this molecule here is called furan. And there's some lone pairs on this oxygen. And we want to determine, is this compound aromatic? What does the oxygen have? Does the oxygen affect our aromaticity here? That's a big question. So the first question, remember, aromaticity has 3 things that we need to check for. And the first thing is a closed p orbital loop. And do we have a closed loop of p orbitals? Well, looking at this diagram, we have an oxygen here that looks to be sp3 hybridized. Remember, if we count up the steric number, there's 1, 2, 3, 4. The steric number is 4, so it should be sp3 hybridized. But we have lone pair next to pi. There's a possibility for resonance, so if it participates in resonance, it will be sp2, which means we will have a closed p orbital loop. But if it's not going to participate in resonance, then we won't have a closed p orbital loop. So we'll just say maybe. Is it planar? That is a yes. It is planar. It is flat. So let me show you what I mean about the 2 possibilities here. There are 2 possibilities for the lone pairs on this oxygen. Let me draw kind of a side-on view of our compound. And I'm going to draw the p orbitals as well. So here are the p orbitals, and I'll shade them in to show the phase. And see, they're all getting lined up and ready. They're getting lined up and ready to make a closed loop of p orbitals, which would create aromaticity. Now, it's possible that the oxygen will stay sp3 hybridized. In that case, the lone pair electrons will be inside of sp3 orbitals. And those lone pairs will not be participating in resonance. Because remember, if those lone pairs want to participate in resonance, they have to be sp2. The other possibility is that the oxygen rehybridizes to become sp2. Let me draw our little diagram again. So if this oxygen rehybridizes to become sp2, then it will get a p orbital on it, and it will keep an sp2 orbital. So there's two lone pairs, so one of the lone pairs will end up inside of the p orbital, and the other lone pair will stay inside of the sp2 orbital. The oxygen itself is sp2 hybridized. It's got one lone pair in an sp2 orbital and one lone pair in a p orbital. So this is a possibility. Now, the question is, which one of these structures is preferred? And it turns out it will do this option if it helps the molecule get to a Huckel preferred number of pi electrons. So let's look at the option of without the oxygen participating. If the oxygen opts to keep its electrons out of the game, then there will be these two pi bonds, and each of these pi bonds will contribute 2 electrons. So it'll be 1, 2, 3, 4, and that is bad. Remember that 4 electrons is anti-aromatic. So it would be preferred actually for one of the lone pairs on oxygen to contribute to the pi system to increase from 4 to 6. And so that's indeed the case. The oxygen is smart. It knows I'll give you one of my lone pairs. Now you'll have 6 electrons in a closed loop so that you'll become aromatic. So this is the best picture here on the right because it creates 6 electrons. So we have 4 pi electrons from pi bonds plus 2 pi electrons from oxygen's lone pair. So in other words, the oxygen will donate the 2 if it will help. If it will help. Let's take a look at another example. Here is pyridine. The question is, where is this lone pair? Well, it depends if the aromatic system needs it. Depends if the pi system needs it. Take a look at how many p electrons there are without the lone pair. There's 1, 2, 3, 4, 5, 6. 2 for each pi bond. So it already has 6 electrons. Does the nitrogen want to contribute its lone pair? No. No more, please. Because 6 electrons is perfect. If the lone pair was contributing, we'd go up to 8 electrons, which is anti-aromatic. So if you look at the side-on view of this compound, here's all the p orbitals lining up. Nitrogen is sp2 hybridized, so it has a p orbital, but it also has an sp2 orbital. And where do you think it's going to put its lone pair? Do you think it wants to put the lone pair in the p orbital or the sp2 orbital? It wants to put the lone pair in the sp2 orbital. That will keep those electrons away from the pi system, not contributing to the 6 that's already perfect. So we don't need to add another 2 to get to 8. That would be bad. So you can see that the lone pair on nitrogen is staying well away from the aromatic system in an sp2 orbital, not contributing towards that 6. Let's take a look at another example on the next page. This is a fun compound. It's got nitrogen and boron in it. So let's take a look at this compound. It could be aromatic. Let's see how. We've got 2 electrons here, 2 electrons here, so that's a total of 4. And we have this lone pair here that could contribute to make 6. The boron is sp2 hybridized. I'm sorry, I'm forgetting an H on that boron. The boron is sp2 hybridized, and it has an empty p orbital, so that could help complete the loop of p's. So the boron is sp2. All it can do is provide an empty p. The nitrogen is sp2 if it rehybridizes and can provide a lone pair in the form of 2 electrons. Perfect. This is, in fact, aromatic. Why? We've got the pi system comprised of the following. 4 electrons from the double bonds plus 2 electrons from nitrogen. So that's going to add up to 6 electrons, and it will be aromatic. If we draw the sort of orbital picture of this, it would look like this, NB. Okay. Draw our little p orbitals, one on boron, one on nitrogen. And we can see that the lone pair, the nitrogen's going to put that in the p orbital so that it can contribute towards the overall count of the ring, at increasing the total count from 4 to 6. So this compound was predicted for decades. Once the frost circle people and stuff had been predicting aromatic compounds, they predicted that this compound should be extremely stable, and it was finally made in 2009. And it turned out to be kind of tricky to make, but they did finally make it and prove what they had already suspected, which is that this is an aromatic compound. And that is amazing. And that is extremely gratifying as a chemist to be able to predict a property, predict a molecule that will fit that property, and then even though it took 30 years to make it, you're finally validated, knowing that you really know that you got it right when you predict something that doesn't even exist yet and then it fits the mold. So something kind of cool about this compound, and we're almost done, I promise, is actually has to do with drug abuse. I don't know why I say that's cool. It's not cool. So let me draw a compound here. This is a compound called fenfluramine. And fenfluramine is a performance-enhancing drug. It's like speed. It's common among athletes, cyclists, Olympic gold medalists that probably shouldn't be Olympic gold medalists. You take this compound and it gives you that boost of energy, that extra boost that's going to get you through that finish line. And so you can see why this kind of compound would be popular among people who need a lot of endurance when they're doing a physical activity. Of course, all of these Olympic teams and stuff, they drug test their athletes to make sure that they're not taking drugs like this, to make sure the game is fair. But imagine you made this compound. Can you see where I'm going with this? We replace the benzene ring with our dummy aromatic ring that we know is still aromatic. It has pretty much similar properties to benzene, but structurally it's different. So it's undetectable by drug tests. And because this compound, these sort of themes were only made in 2009, the technology is not quite there yet to catch this sort of drug. It would likely have the exact same effect as regular phenfluramine, but because of the modification to the aromatic ring, using this structure that we see above, it would be undetectable. Now, another kind of clever thought to think about this, and this is my billion-dollar idea, so don't steal my billion-dollar idea. But there's a lot of pharmaceutical compounds out there, expensive ones, things like Lipitor and other compounds that are taken by millions and millions of people around the world to treat health conditions, prescription drugs. Now imagine you took a prescription drug and replaced one of the benzene rings in the prescription drug with one of these rings. Well, it should still be an active drug, right? It should still treat whatever the condition is. It's likely that simply changing out the benzene ring for this ring is not likely to change the effect that much. However, because this sort of technology is so new, nobody ever thought of this when they were patenting the drug. So this will allow you to copy someone else's drug, get all of their hard work and stuff, and claim all the rewards, because then you can resell it as your own. And technically, I mean, they can't claim that you didn't copy them. You changed it after all. They had their chance to say, you know, this is our drug. These are all the modifications that you are allowed to make, and these are all the modifications you're not allowed to make. And because this is such a new technology, a lot of these people maybe forgot to include this in their writing as like changes to the aromatic ring, for example. So there's my $1 million idea. Very unethical, but it's really cool to think about the possibilities of taking benzene rings, which are so common, and replacing them with benzene analogs like this. Okay, just a final thought about aromaticity. Oh, there's Lance Armstrong. I was going to show him there. So yeah, he loves my idea here. He's like, right on, you do that. Final thought about aromaticity has to do with linked aromatics. So you can have multiple aromatic rings linked together. And so what we can see here is that we have two separate aromatic systems here. We have one in yellow and then one in green. So you would not add up all of the electrons in both of them. Instead, treat them separately. They're two separate aromatic systems. Versus the molecule on the right, is just one system. See how these two aromatics are kind of linked together with this bond, versus this is all just connected, fused together. Let's try and count how many systems are in this crazy molecule down here. Okay, we definitely have one over here. We have another one over here. We have another one right here. We have another one right here. And what about this guy? Is this guy aromatic? No, because we've got sp3 hybridized atoms in the way, so that blocks the planarity. So that is a non-aromatic thing dangling off there. And we can also add up all of the electrons in each of these aromatic systems. So remember, each pi bond counts for 2. 1, 2, 3, 4, 5, 6. So this one's got 6 electrons. This one also has 6 electrons. Let's count this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is a golden number. It's even, not divisible by 4. That's aromatic. Okay, let's go down here. 6 electrons in this one. How about in green? How many do we have? 1, 2, 3, 4, 5, 6, 7, 8. That would be anti-aromatic, but we've got some lone pairs on the nitrogen. Those can contribute, so that'll bring us up to 10. Thank goodness for those smart heteroatoms knowing when to donate their lone pairs if it helps. This guy here is another 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what about this big guy? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, it's an even number, not divisible by 4. So that'll be 14 electrons. That's aromatic. And then this guy is not aromatic at all. No closed loop. of p orbitals because we have some sp3 hybridized carbons in there. Okay, I know this has been a lot of information in a very short period of time, but the most important thing is that you're able to predict whether a compound I give you is aromatic, non-aromatic, or anti-aromatic. So I'll have a lot of practice on that in the post-lesson quiz, which you should take right now, and in the problem set. So there'll be lots of practice to predict aromaticity. Bye for now.